So we've talked a little bit about direct comparison, and direct comparison can be a little bit complicated to show that something is bigger than something else or that something is smaller than something else. And so to sort of deal with some of the intuition that we have in a more efficient way, we are going to talk about the limit comparison test. In case you wanted to write notes on this with this lovely little sheet, you could pull this up. It's the second page of our test for comparison. So the limit comparison test says if you've got two sequences that are positive for all n, then if you take the limit as n approaches infinity of their ratio and you get some positive number, then the two series, the series of a sub n and the series of b sub n, either both diverge or both converge. So they behave the same, basically. And that's really lovely because that tells us basically that our intuition is true, that if something looks like it's going to behave like 1 over n, then it probably is. And if something looks like it's going to behave like 1 over n squared, then it probably is. So let's look at this one right here. That's supposed to be a 1, n equals 1. And it's got the series of 5n plus 1 over 3n squared. So first of all, we want to think like, well, what do I think is going to happen to this? And because I have a first degree over a second degree, what I think is going to happen is that it's going to behave like 1 over n. And so I think that means that it's going to diverge. This one, on the other hand, is like 1 over n to the 4th. So I think that this one is going to converge. Okay. So in order to show that these converge or diverge using the limit comparison test, we can set up a limit and say the limit as n approaches infinity of one divided by the other. So the one we want to know about divided by the one we already know about. And if we just get some constant out of this, then we know that they both diverge because we already know that the series of 1 over n diverges. It's a divergent p-series. So you can see p-series become really important to know really well because we use them when we're doing limit comparison and direct comparison. Okay, multiplication by reciprocal becomes really important. And you get the limit as n approaches infinity of 5n squared plus n divided by 3n squared. I just multiply by reciprocal. And that is same degree over same degree. So that equals 5/3. That limit equals 5/3. Thus, by limit comparison, this series diverges. And that's because we compared it with the divergent p-series of 1 over n, the harmonic series, and we saw that the limit as they approach infinity is a constant, it's just 5/3, so they must both diverge. In contrast, for this one, let's take the limit as n approaches infinity of 1 over n to the 4th minus 7 all over 1 over n to the 4th. Again, multiplying by reciprocal. We get the limit as n approaches infinity of n to the 4th over n to the 4th minus 7. That is pretty clearly 1. And 1 is a positive number, so by limit comparison, this series converges. And the reason this one converges is because we compared it to a convergent p-series, 1 over n to the 4th. So your first step with limit comparison is to say, well, what do I think this behaves like? First degree over second degree, seems like it probably behaves like 1 over n. So let me compare it with 1 over n by taking the limit as n approaches infinity of the sequence I'm interested in divided by the sequence I already know about. If you get a constant, you know they both diverge. Over here, I think it behaves like 1 over n to the 4th, so I think it converges. So I will find the quotient of the two, take the limit as n approaches infinity, and get a constant. Thus, they must both converge. So that's the limit comparison test, one of my favorite tests for convergence.